Hello students, welcome to today's class. Today we will be studying about the fascinating chapter of center of mass. Now on previous occasions when I tried to make you understand the concepts of Newton's laws of motion, and when we studied about mechanics in general, like the parabolic path of a projectile motion or the motion of a body along a straight line, as we often study in Newton's first law, also in gravitation, the concept of the point masses. uh, Let me just reiterate that fact which I had said during that time, that whenever we are dealing with any kind of bodies in the domain of classical mechanics, that is in the region of Newtonian mechanics, when Newton's laws are valid, I had also told this before to you that there is a certain domain, like for velocities which are comparable to the speed of light, where Newtonian mechanics or the Newton's laws do not hold any longer. So that is outside the Newtonian mechanics domain. Similarly, we can also think of reference frames that are accelerating, that are not at rest or that are not at a uniform velocity. In those accelerating frames as well, Newton's laws are invalid. So when I say Newtonian mechanics or classical mechanics, I basically mean this region where these exclusions are not applicable. Now whenever we study about this kind of Newton's laws, this kind of motion of particles, projectiles and so on, all the time we write these formulas. Like you are familiar with some formulas like F equal to ma. This is one of the common formulas you have been studying since lower classes. So whenever we do this, or similarly if we are studying gravitation, we write G equals to these are the kind of formulas that you are familiar with. Now, in all these cases, when we talk about the bodies, when we talk about the masses, we consider as if the entire mass of the system is concentrated at a certain point of the body, and that point we call it to be the center of mass. So if this is my body and the mass is uniformly distributed, that means the mass per unit volume, which we call the density rho, that is constant throughout the body. In such cases, we can consider as if the entire mass is concentrated at a single point, the point which has got a very high density. The volume is infinitesimally small, and therefore when the entire mass is concentrated at that point, it means that the density is infinitely high. So those factors we will rule out for the moment, but what we will consider is entire mass of the system, instead of being distributed throughout the body, is only concentrated at a certain point. Instead of being distributed throughout the body, we can assume it to be concentrated at a single point. And how can we assume that? Well, if that particular point which I have represented here, and I consider that point and I name it O, and if I calculate the clockwise and the anti-clockwise movement of all the particles, so there are different particles in the body, I consider the clockwise and the anti-clockwise movements and so on for all these individual particles, and if that sum of moments turns out to be 0, then we can say yes, that point is my center of mass. We will study this definition in class 10. Now here we will be doing something new. We will be denoting the center of mass via the position vector. So suppose I have 2 point masses here, which have got masses m1 and m2. So these are 2 point masses, and I want to find out what is the center of mass of this 2 mass system. Where is the center of mass for this 2 point masses combined lie? So first of all, what I do is I consider a coordinate system. I let this be the x, this one the y, and this one to be the z axis. So obviously this is my origin. Now what is the position vector of the 2 particles with respect to origin? Position vector of m1 with respect to origin, let that be r1, and position vector of m2 with respect to origin, let that be r2. So these are the position vectors of these 2 point masses. Now suppose that the center of mass lies somewhere here, then the position vector of that center of mass with respect to the origin, I denote it as r center of mass. Then what does the definition of center of mass tell me, as I said, sum of the moments should be 0. So that means if I consider the entire system as 1, that is if I consider the total mass of the system, the entire system as 1, total mass into the position vector of the center of mass of the system. This is the total mass, so that means this is the entire system times position vector of the entire system. That is equal to mass of the individual particle times its center of position vector with respect to origin plus mass of this individual particle times its position vector with respect to origin. So these are the individual moments, the individual masses multiplied with their corresponding respective position vectors, and on this side we have got the total mass and the position vector of the center of mass. From here we can simplify and write it down that the position vector of the center of mass is m1r1 plus m2r2 divided by m1 plus m2. So this is in vector notation. That means this position vector, this is the vector notation of the position. That means we can find it out actually its magnitude as well as its orientation and direction in space if we use this formula. But this is only for a two-body system. We can have more than two particles. We can have more than 2 point masses. So what will happen in that case? We will study it now. So this is one formula that you must remember. We will need it later on. Now suppose that I have say this kind of a shape of rock which is made up of a number of particles, many particles. It is made up of n number of particles. I do not exactly know how many, so n number of particles. Each one has got its own individual position vector with respect to the origin. So if I say this is particle 1, then this is R1. If this is particle 2, then this is R2. If this is particle 3, then this is R3, and so on. If this is the nth particle, this position vector will be R1. Then for this kind of systems, what will be that expression for the center of mass? The expression for the center of mass will be one particle times its position vector plus second particle times its position vector plus third particle times its position vector plus fourth particle times its position vector, and so on. It will go on until the nth particle times its position vector. And this entire thing will be divided by what? The sum of the masses of individual particles. Now what is this sum? That is the total mass of the body, so I call it capital M. So 1 by capital M comes in the front times I have M1 R1 plus M2 R2, and so on. It goes on up to the nth particle. Now there is this general way to write it. How can we write this? We can write this to be 1 by M times summation over I ranging from 1 to n, mi Ri. So if you are familiar with computer programming, you know we often while solving programs on nested loops and so on, we use this kind of variables where we use summations. So basically this is the center of mass for a system which has got more than two particles, and the number of particles, it may be any number, we don't know it, so n particles. So in that case the summation will run from 1 to n times mi Ri vector. So when I is 1, it's m1 r1, when I is 2, it's m2 r2, when I is 3, it's m3 r3, and so on. We will keep on adding it up and divide it by the total mass to find out where is the center of mass located, which I have represented. Okay, I have not represented it in this diagram. So say suppose the center of mass is located somewhere here. Then what we found out here, the RCM, that is basically this position vector with respect to the origin. Remember, this holds good only for a system of discrete particles. By discrete I mean the particles are individually separated. Okay, they are not in a continuous distribution. Let me give you an example. Take a glass of water. In a glass of water, can you say that the water is made up of discrete particles? it's as if one continuous fluid is present within the glass. But if I give you a small pouch filled with, say, the coins, the currency coins that we use, 1 rupee, 2 rupee coins, there each of the coin is a discrete particle. You can separate it, you can count it, it's countable. But in water, we cannot count and say, yeah, there are this many number of particles or this many number of molecules and so on. So in that case, when I write this expression, remember this is for a system or a distribution of discrete particles only, not a continuous distribution. Now what is going to happen if it is a continuous distribution? As I said, say if it is a glass of water, in that case what will be the expression for the center of mass? In that case the expression for center of mass will be, once again, 1 by m, and here what did we have? We had summation of MIRI. This is what we had when it was discrete particles. So if it is a continuous system, how do we do summations for continuous systems? Instead of individual addition, we do integration. So this will be integration of R dm. So here dm is just a small mass. So say this is a rod, okay, and there's a continuous distribution of mass. There are not individual discrete particles. Where is the center of mass located? So what we do, we consider a very small amount of mass. This is a small amount of mass d, and we will assign a position vector to that dm with respect to the origin. So this is my coordinate system with respect to origin. This is the position vector, and this is a small amount of mass dm. So I have the r of that dm, and this I am going to integrate for the entire length of the rod. Say in this case, as we are talking about the rod, it is from 0 to the total length of the rod. For other cases it can be different. So I am not writing out this limit because this is a general formula. So if we are finding out center of masses of this kind of continuous mass distributions, what we will do, we will take a small amount of mass, we will locate the position vector of that small amount of mass with respect to our chosen origin of the coordinate system, and then we will integrate that over the entire dimension of the system that we are considering and divide that by the total mass of the system. Basically, total mass of the system can also be written as integration dm, because when you do integrate the small bits of mass dm, you also get the total mass, and this is equal to the position vector. So this expression is for a continuous mass distribution. There we have to do the integration. Now I was saying something to you. I told you that in the Newtonian mechanics we always, or in the gravitation when we were studying, I said this, that when we study about the law of gravitation, about how two planets or two bodies attract each other, we consider as if the entire mass is concentrated at a point. And I had told this to you giving an example that if there are these two planets, when we write down the law of gravitation of g m1 m2 by r square, we consider as if the entire mass is concentrated at this one point, because points, mathematically points have no dimensions. So when we write that we find out what is the distance between them, d, then in that case g is simply, sorry, not g, force is simply g times the two masses concentrated at the 2 points divided by whatever is the distance squared. But if we do not do that, suppose this is one mass, this is another mass, there are two masses somewhere out there in space, and since this is a bigger mass, it will exert a greater gravitational force, and when it exerts a gravitational force, if I consider the mass to be distributed throughout the planet or throughout the body, then what will happen? So this is the center of mass. So say this distance be d1 and this distance be d2. So obviously we can see d1 is smaller than d2. Therefore, if I say that the force that this closest surface is facing, if I say it to be F1, then F1 is G m1 m2 by d1 square, and the force this distant surface is facing due to this body, that would be G m1 m2 by d2 square. Now since d1 is smaller than d2, obviously F1 will be bigger than F2, or the near side of the planet will face a greater amount of force on the further side, so that will lead to a rupture of the planet. So that is why, in order to avoid this kind of problems, what we do is we consider as if the entire force is acting on its center of mass, and as if the entire mass is concentrated at the center of mass, obviously for bodies with uniform densities. So for that, how are we going to establish that? We will be deriving it. So suppose there are these 2 point masses within an oblong shaped body. So everywhere else is empty space, there are just these 2 point masses m1 and m2. Alright. Now on m1 there is an external force acting, say I call it F1. This is the external force. External force means someone from outside is exerting it. And similarly on m2, some external force F2 is adding. So these are the 2 external forces. And on m1 there will also be an internal force. So that will be force on 1 due to 2. This is the force that m2 is exerting on m1 by virtue of its own mass. Similarly, the second mass will feel a force F on 2 due to 1 due to the mass m1. So the upper ones are the external forces, the lower ones are the internal forces. What is the total force acting on system? Total force is force external plus force internal. Force external is F1 plus F2, and force internal is F12 plus F21. Now since these 2 forces are action and reaction pairs, this is the nature that they follow. F on 1 due to 2 is equal to negative of F on 2 due to 1. So when I add these 2 up, that becomes 0. So this becomes 0, and what we are left with is F1 plus F2. But we know another thing as well from Newton's law, that the total force acting on a system is equal to the rate of change of momentum of the system, and momentum is basically mass times velocity of the system. So I can write this down as well. So now if I consider this system and this force, then F1 plus F2, which from now onwards I will write simply as force external, that is equal to ddt of m1 v1 plus m2 v2. That can be separated as ddt of m1 v1 plus ddt of m2 v2. This can be written as, what can we write down for velocity? We know this thing again from basic calculus, that velocity is rate of change of position with time. So for v1 we can write dr1 by dt, and here we can write ddt of m2 times dr2 by dt. Okay. Now what we will do is we will take m1 outside and m2 outside because they are constants. So what we will be left with is d dt twice acting on r1. So that basically looks like this m1 times d2 dt2 of r1 plus m2 d2 dt2 of r2. Okay, so I will have to make some space. So this is the expression I have got, that m1 d2 dt2 of r1 plus m2 d2 dt2 of r2. So I can basically write this down as that force external is equal to the double derivative of m1 r1 plus m2 r2. I can write it down like this. Now what I will do is multiply the numerator and denominator by m1 plus m2. So this will become m1 plus m2 times d2 dt2 m1 r1 plus m2 r2 by m1 plus m2. Now if you remember, this is the expression for center of mass of a two-body system. So I can substitute that here, and this is the total mass of the system. So this becomes total mass times d2 dt2 of the center of mass of the system. And on this side we have the force external. So from here we know this by now, that from basic calculus the second derivative of the position is acceleration, because we know that the first derivative of the position is velocity and the first derivative of velocity is acceleration. So instead of velocity, if I write dr dt, that means the second derivative of position becomes acceleration. So from there what this basically is mass times acceleration of the center of mass. So we get the familiar form of Newton's second law, that the external force acting on a body, irrespective of the internal forces that they exert on each other, is equal to the total mass of the body or the system times acceleration of the center of mass. So that basically means we don't have to consider all the individual particles and find out all their individual velocities and accelerations and positions. All we need to know is, by using this expression, where is the center of mass of the system. And once we find that, we can assume as if the entire mass is concentrated at the center of mass, and as if it is only the center of mass which is accelerating. And this gives me the total external force, F external, which is acting on the system. We studied this in Newton's law, that a change in the state of rest or motion is brought about only by an external force. So that is once again proven here, because internal forces form action and reaction pairs and they cancel each other. Let me just solve some examples or some numericals based on the center of mass for you. So there is this numerical which says that there are some masses, m1 2 gram, m2 2 gram, m3 1 gram, m4 1 gram. It is said that they are placed at the corners of a square of side L. The question says that where is the center of mass located with respect to m1. They asks for the location of the center of the mass with respect to m1. Now here we will do one thing. Obviously, first of all we will draw some kind of coordinate system. So once we draw a coordinate system, since they have asked us to find out the center of mass with respect to m1, we will play a trick. We will consider that m1 is located at the center of mass. From here, if we construct a square of side L, so this coordinate is L, this coordinate is L, and this coordinate graphically is L comma L. This one has a y value 0, this one has a x value 0, and this is origin, so it is 0 comma 0. And there are the four particles which are situated. So it is not said that who is situated where, so I just move in a cyclic manner. Say m2 is here, m3 is here, and m4 is here. These are the four masses situated at the corners of the square. So we have to find out the center of mass with respect to m1. So that means we basically need to find out the x and y coordinate. Say the center of mass is somewhere here. So it will have some x coordinate and some y coordinate. This is what we need to find out. So first of all, when we are finding out x coordinate, x center of mass is equal to m1x1 plus m2x2 plus m3x3 plus m4x4 divided by total mass. So m1's x coordinate is 0 because it is at origin, so this cancels. m2's x coordinate is also 0 because this is also on the y-axis. m3's x coordinate is here, L, and m3's mass is 1 gram, so it is 1L. And m4, it has a mass 1 gram, and x4 is the x coordinate of m4, and that is also L. And what is the total mass? 2 plus 2, 4, plus 2, 6. So this becomes 2L by 6, that is L by 3. This is the x coordinate of the center of mass. And what would be the y coordinate of the center of mass? In a similar way, you can find out y coordinate will be m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 divided by total mass. So m1's y coordinate is again 0 because it is at origin. m4 lies on x axis, so its y coordinate is also 0. And these two have y coordinates L. m2 has mass 2, m3 has mass 1, and total mass is 6. So that basically means that this center of mass has the coordinates L by 3, L by 2. So this is a way by which we can find out the center of masses of the different systems. And as you saw, I solved for x and y coordinates separately. If this masses had some orientations with respect to the z-axis, then I could have solved it with respect to z-axis as well. But it is said as square. They haven't said it's a cube. So square is a two-dimensional figure. So I could have taken, instead of xy plane, I could have taken the yz plane or the xz plane. But if they had told me a cube, then similarly I would have found out ZCM, and then this would be a three-dimensional coordinate giving me some point in space. And you can find it out separately for each of the coordinate directions, as I had said previously as well, when you will calculate momentum conservation equations, that you can treat each coordinate direction or system as an independent one, as if it does not depend on the other two coordinate systems. That is the way you can find it out.